we are going to start a new optical phenomena, that is refraction. Refraction, okay. In the beginning itself, in the first lecture itself, okay, we discussed about this phenomena, that is reflection and refraction. Both happen simultaneously together, okay. How? How it happens? Okay. When light traveling in one medium, enters into another medium, then its velocity, its speed changes, and it may also deviate from its path. Okay? Look at this statement. It may also deviate from its path. It may. The deviation is not necessary. Okay, sometimes in most of the books it is defined like this. When light enters from one medium into another medium, okay, then it bends. That bending is known as refraction. Okay. In refraction, bending is not necessary. It's not always that bending happens. Okay. It may happen, it may not happen. We will look at the cases where it does not happen. Refraction is transmission. That's it, transmission. Light in one medium, it goes into another medium, it transmits into another medium, that is refraction, that's it. Okay? Okay. It happens at the interface. Okay? In refraction, speed and wavelength change, okay, but frequency never changes. Okay, frequency never changes. Okay, it is always equal to frequency of the source, okay, which produced it. Okay, very simple general introduction about refraction. Now, so important thing is that its speed changes. That means its speed should change. Its speed should change. Then only we say that there is refraction. Now, how the speed depends on medium. Okay, the speed of light in a medium, okay, depends on a property of medium which is called refractive index. Mu. Okay, and is defined as refractive index is equal to speed of light in vacuum over speed of light in medium. Okay, we define it like this. Mu is equal to C over V. This is C and this is V. We are going to use this symbol for refractive index. Okay, it has various symbols. It does not have one common symbol. Okay, in many books you find it written as N for refractive index, but you see it makes no difference. Okay, we do not really have to be too much bothered about the symbols and all. We have to understand this meaning. This is how we define the refractive index of a medium. So every medium is going to have a certain refractive index. Depending on the refractive index, light is going to have velocity in that medium, depending on the refractive index. What will be velocity? It is going to be equal to c over mu. This is the speed of light in that medium. Now, certain other important things. The speed of light is maximum in vacuum and equal to C is equal to 3 into 10 power 8 meter per second. It's a constant. Okay. This is the speed of light in vacuum. Okay. In any other medium, okay, V is always less than or equal to C. V is always less than or equal to C. Okay. So mu is always more than or equal to 1. What it means? That means the refractive index of any medium, it is always going to be more than 1. Always. Okay? Because this is maximum. In any other medium, the speed is always going to be less than this speed in vacuum. So mu is always going to be more than or equal to 1. Okay? Mu of vacuum is equal to 1. Exactly equal to 1. Okay? Mu of air is approximately 1. Okay, so we can say that the speed of light in air is approximately same as that in vacuum, equal to C. Okay, now there is one other standard material, that is water. This is equal to 4 over 3. 4 over 3. Okay, all right. Note it down. Then let's look at one other property and then we start doing problems. Okay. All of this I'm sure should not be new to you. You must already have done this earlier also. Okay, but we are just revising it quickly. Okay. Medium having slower speed of light. Speed of light is called denser medium. And those having relatively faster speed are called rarer medium. Denser medium and rarer. Denser medium has nothing to do with the physical density, mass by volume. Understand this. This is optical density. This is not the physical density, mass over volume. No. So I have two mediums. Okay. If I compare the speed of light, in one medium speed will be slower as compared to the other one. The other one it will be faster as compared to the first one. Okay. Medium in which the speed is slower, it is denser medium. Denser medium. The medium in which speed is relatively faster. I am comparing to C. It can never be more than C. But I am comparing two medium. The medium in which the speed is faster is rarer. The medium in which speed is slower is denser. Okay. So You see, mu is equal to C over V, V is equal to C over mu. So V is proportional to 1 over mu. Okay, so mu increases, velocity decreases, speed decreases. Mu decreases, okay, velocity increases. Okay, that means a denser medium will have higher refractive index. Okay, so if I have two mediums of different mu value, the one having higher refractive index of one medium is, let's say, 2, the other medium is 3. The medium having refractive index 3 will be denser. It will be denser medium. Okay, higher the refractive index, denser will be medium, and then the slower will be speed. Okay, remember this. Now that's it. Let's do a few problems. Remember all these points. All these points you have to remember. We are going to have problems based on whatever we discussed now. Okay. Okay. Now let's see. Okay. Ready? Problem. First problem. What is the speed of light in water? What is the speed of light in water? Okay. Speed of light in water. First question. Second question. Speed of light in glass is 2 and 10 power 8 meter per second. Okay. What is the speed of light in mica if refractive index of mica relative to glass is 0.8. Okay. Look at these problems. Very simple problems. Okay, this is medium 1. Its refractive index is mu1. This is medium 2. Its refractive index is mu2. Mu1, mu2. Okay. Let's say that I have this light. This light is traveling in medium 1, and then it enters this medium 2. It enters medium 2. Okay. Frequency of light here is f1. Okay. f1, speed is v1, and wavelength is lambda. Let's say. Now this is the interface. Okay. I am explaining the problem. Explaining it. This is the interface. At this point, some part of the light will come back. This is reflection. Okay. Let's say that the frequency of reflected light is f2. Okay. Or let me write it here. This is some part will be transmitted to the other side. There is a diffraction. Frequency of this light is f2. Speed is v2, and wavelength is lambda 2. Let's say. And frequency of this light, some part will come back. Okay. It is reflection. Frequency here is, let's say, f3. This is speed is v3, and wavelength is lambda 3. Okay, find relation. Find relation between frequency, speed, wavelength of different light. Wavelength between different light. So this is my incident light. Okay, this is the interface. It separates two mediums. Some part is reflected, some part is transmitted. This is refraction, this is reflection. I have to find relation between the various quantities. Okay, how they are related. Okay, let's do this, and then we are going to have few more problems. Okay, pause the video, forget about it. Note down the problems, forget about it. No, forget about the video. Pause the video, note down the problems, pause the video, then solve it. Okay, very simple problem. Introductory 0 level problems. Okay. Let's try to solve it correctly in your first attempt. First question. Okay, I'm going to discuss it now. We define refractive index as C over V. Okay, so V will be equal to C over mu. What is C? The speed of light in vacuum. It is written here. 3 and 10, 8 over mu. It is water. What is refractive index of water? This is something that you can remember. Okay. Generally, it is given in the exams, but it's better if you remember. It's very simple to remember. 4 over 3. That's it. Okay. 4 over 3. So that becomes 9 over 8 and 10, 8 meter per second. It becomes 2.25 and 10, 8 meter per second. As simple as that. Okay. Next problem. Do you find something weird about it? About the data especially? Here we are saying that in any other medium, speed is always going to be less than c. For that reason, mu is going to be more than or equal to 1. Here I am writing 0.8. Is this some kind of mistake? Is this a mistake here? I am writing it as 0.8. Can a medium have 0.8 refractive index? No, that is not possible. Absolute refractive index. This is known as absolute refractive index. With respect to vacuum, this is always going to be more than 1. Here, this is a relative refractive index. Refractive index relative to glass. Okay. So if I have two medium, refractive index of medium 1 with respect to medium 2 is equal to refractive index of medium 1 over refractive index of medium 2. Okay. That means what is given here is actually a relative value. This is not the absolute value. So this can have any value. It can be less than 1, it can be equal to 1, it can be more than 1. But the absolute refractive index, it is always more than 1. Okay, you should understand this point. So now, what is given here is refractive index of mica over refractive index of glass is equal to 0.8. Okay, now what I have to find? The speed of light in glass is this. What is the speed of light in mica? Okay, so the speed of light, the speed of light in mica is equal to C over mu of mica, and the speed of light in glass is equal to C over the speed in glass, mu of glass. I mean, if I divide both, the speed in mica over the speed in glass is equal to, you see this will be reversed, it becomes mu of glass over mu of mica. Okay, so now the speed in mica is equal to, now reverse of this, so this becomes 8 over 10. Okay, so when I reverse it, glass over mica, 10 over 8. So this becomes 10 over 8 times the speed in glass. What is the speed in glass? 2 into 10, 8. 2 into 10 power 8 meter per second. This will be answer, okay? So 4, 2.5 into 10 power 8 meter per second. This will be speed in mica. Okay? Now let's relate these things. They are very important. They are very, very important. Okay? And the result we have to actually keep in mind. We have to remember it. Okay? I'm not asking you to memorize it, but if you simply keep it in mind, it will remain. Okay? because it's a very simple result, almost obvious. First of all, let's relate the frequency. Understand this. No matter what happens, frequency never changes, either in reflection or refraction. Okay, the wave, light is a wave. So some source produces it. So with whatever frequency the light is produced, that frequency remains constant all the time. It never changes. Okay, so here F1, F2, F3 is going to be constant. F1 is going to be equal to F2 is going to be equal to F3 is constant. Frequency is constant. These two are same mediums, incident light and reflected light. They are in same medium. So when medium is same, frequency is same everywhere. In these two mediums, frequency is same and speed also is same. Speed is same. Frequency is related with speed. Okay, speed is equal to frequency times wavelength. Frequency times wavelength. Okay. Now, if medium is same, speed is same, frequency is same, so wavelength will also be same. It is the same medium. Okay. So this is one relation. The other one will be V1 is equal to V3, lambda 1 is equal to lambda. Because it is the same medium, frequency, speed, wavelength, everything will be same. Now what about here, between these two mediums, mu1 and mu2, okay, frequency is constant. Frequency is equal to V over lambda is constant. Frequency is V over lambda, it is constant. Okay. V is equal to C over mu. Understand this, very, very important. Very important result. We just discussed it. C is going to be equal to, okay, or write it like this. Mu times V is going to be C is equal to constant. Okay, that means mu1 V1 is equal to mu2 V. Okay, you understand this? You understand this? And now from here, I'm going to write lambda, or if I write it as V is equal to F times lambda. Okay, this is mu1. Okay, F times lambda 1 is equal to mu2 F times lambda 2 is equal to C is equal to constant. Okay. So I have this relation. Okay, if a given light ray, a given light passes through various mediums, okay, mu1, mu2, mu3 and all that. Okay, so I have many media. Okay, I have this light ray. It passes through several mediums. Okay, this is mu1, this is mu2, this is mu3, this is mu4. Okay, so the speed here is V1, the speed here is V2, the speed here is V3, the speed here is V4. Okay, wavelengths are lambda 1, lambda 2, lambda 3, lambda 4. Lambda 4. Okay, then this relation exists. Okay, what is this relation? Okay, mu V is constant. Mu V is constant. Okay, mu V is constant. Okay, that means mu1 V1 is mu2 V2 is equal to this. Okay, now from here mu V is what is V? V is F lambda. F lambda. Here I can write mu F lambda is constant. F is already constant, it never changes. That means mu times lambda is also constant. So mu times v is constant, mu times lambda is also constant. Okay, mu lambda is constant. Okay, so mu 1 lambda 1 is mu 2 lambda 2 is equal to that. Understood? Okay, good. Okay, we are going to look at one other relation also. Okay. Okay, it's like this. Light of frequency 4 into 10 power 14 hertz. Light of frequency 4 into 10 power 14 hertz is traveling in glass. In glass, mu is 1.5. Okay, it is traveling in glass. Okay, what is its wavelength in glass and in water? In water, mu is 4/3. Okay, what do you think? Okay, try to answer this. Can you answer it? We are doing it quickly. Okay, we are doing it quickly because this is something that we have done already. Already we have done. Understand this. I have this light of frequency. This is the frequency. This is the frequency. No matter, I have this light. That light is passing through several mediums, one after the other. No matter in which medium it enters, its frequency is going to be constant. So if the frequency of light is this much in glass, it will be in water also. It will be in water also. Do you understand this? Okay. Same frequency in water also. Okay. Now, how to find wavelength? Speed is equal to f frequency times lambda. Okay. Now, lambda is equal to speed over frequency. Speed is c over mu times f. And that's it. That's what we have to do. Okay. So, in the first case, lambda in glass is equal to 3 into 10 8 over mu is given. Mu is 1.5 times. Frequency is given 4. 4 and 10 14. Okay, this becomes 6 and this becomes 0.5. Okay, 0.5 into 10, this becomes minus 6. That's it. Okay, this will become 5000 into 10 power minus 10. This is meter, this is meter. This becomes 5000 angstrom. 1 angstrom is 10 minus 10 meter. Similarly, I can find it in glass also. Okay, similarly, we can do it in glass also. A general, simple, okay, brief introduction about refraction. Okay, simple, brief, general. Okay, get it? Now, let's look at one other very important law related with refraction. Okay, it is law of refraction. Okay, laws of refraction. Laws of refraction. Okay, let's say that, okay, I have these two mediums. This is medium 1, its refractive index is mu1. Okay, and I have this medium 2. Medium 2, refractive index is mu2. And this is interface. I have a light ray which is traveling in medium 1. As long as light travels in one medium, it travels in a straight line. Okay. At this point, medium changes at the interface. This is known as point of incidence. Now, if I draw a normal here, okay, this is my normal here. Okay. This is incident ray. Okay. This is the normal. Okay. This is the original path. Light was traveling in this direction. At the interface, it will enter into the second medium. And when the medium changes, generally the path changes. Generally, okay. So the light is going to deviate from this path. In one special case, it does not change. We will look at that case. Okay, we will see. But let's assume that generally it changes. Okay, so it will deviate from its original path. Let's say that it starts going in this direction here. Okay, this is known as refracted ray. Okay, this is point of incidence. Angle between incident light and normal. This is angle of incidence. Theta1 is angle of incidence, and this is theta2, angle of reflection. Angle of incidence, angle of reflection. This was the original path of incident light. It bends, it deviates from this path. This is known as deviation. Okay? Now, first law is incident light, normal. Okay, I'm not writing everything, I'm just dictating. Okay, you should keep on writing, okay, make your notes. Incident light, normal at the point of incidence, and refracted light are in same plane. This is same as the law of reflection. This first statement is common in reflection as well as refraction. Okay. The second law is mu1 sine theta 1 is equal to mu2 sine theta 2. This is known as Snell's law. Refractive index into angle in that medium. Medium 1, refractive index is mu1. What is the angle in the same medium? We are measuring angle from normal. We are measuring angle of incidence, angle of refraction from the normal. This is my normal. Medium 1, refractive index of medium 1 is mu1, angle is theta 1. So mu1 sine theta 1 is equal to mu2 sine theta 2. Refractive index into times the angle, sine of that angle. The product remains constant. Okay? The product remains constant. Mu1 sine theta 1 is mu2 sine theta 2. This is known as Snell's law. We are going to solve problems based on Snell's law. Now there are some special cases. The first special case is normal incidence. Normal incidence. Okay. Now I have two mediums, mu1 and mu2. Light is incident normally on the interface here. This is my incident light. It is along the normal. Point of incidence, if I drop a normal, then incident light is along the normal. What will be theta 1? Theta 1 is 0. Okay. So, sin theta 1 is 0. Mu 2 sin theta 2 is mu 1 sin theta 1 is equal to 0. That means theta 2 is 0. Angle in the second medium will also be 0. Okay. That means the light will pass without deviation. What will be deviation? 0. There is no deviation. In this case, there is refraction, there is transmission. Light is entering into second medium, but there is no deviation. In all other cases, there will be deviation. Okay. Now, second, light going from denser to, or let's say rarer to denser medium. Okay, we are looking at two general cases. You see, light goes from one medium to another medium. Okay. Change in medium happens when refractive index changes. If both mediums have same refractive index, let's say I have water, it has some refractive index, and if I have some oil which has same refractive index as water and that oil have same refractive index. For us, they are two different mediums, but for light, they are same. Okay, so if light goes from water into that oil, it will not experience any change. Okay, so when we say that medium is changing, that means refractive index must change. Only then we can say that for light, medium has changed. If refractive index does not change, then that means medium has not changed for light. Okay, that means out of two medium, if refraction is happening, out of two mediums, light going from one to the other medium, one is going to be rarer, the other is going to be denser. So we are taking this first case where light going from rarer to denser medium. Okay, let's say that I have this light. This is my rarer medium. Its refractive index is mu1. Rare. Okay. This is my denser medium. Denser medium mu2. Okay. Light is incident here. In the rarer medium, this is the interface. This angle is theta 1. I want to find what will be theta 2. Okay. Then I will write mu1 sin theta 1 is equal to mu2 sin theta 2. Mu2 is denser, that means mu2 is more than mu1. The product has to be constant. Okay. So mu2 is more than mu1. So sin theta 2 should be less than sin theta 1. Okay. Theta 2 should be less than theta 1. Refractive index times sine of this angle. The product is constant. Mu1 sin theta 1, mu2 sin theta 2. They have to be same. So if mu increases, sin theta should decrease. That means theta will decrease. Okay. We always measure theta from normal. Okay, understand this. So this is the original path. Okay. This whole angle is, this is theta 1. This whole thing will be theta 1. Now the angle is going to be smaller. Angle from normal. Okay. So now this is what the angle will be. This is theta 2. It is smaller than theta 1. Okay. Look at the deviation. This is the original path. Light is deviating like this. Okay. Light is going towards the normal. Light bends, light deviates, light is bending towards the normal. Okay. So when light goes from rarer to denser medium, what is the result? It bends it bends towards normal. It bends towards normal. In special case, we have to remember it. Okay, you should memorize it. It is very helpful. Okay, if you remember it. Now the next case, light going from denser to rarer medium. Okay, light going from denser to rarer medium. Okay, let's draw this figure again. Okay, let's say that I have this denser medium. It is mu1, and this is rarer medium. Rarer. mu2 is less than mu1. Okay, so I have one denser medium and one rarer medium. Light is going from denser into rarer. Okay, so let's say that this is my denser medium here. This is denser medium. mu1. Angle in this medium here is theta 1. Theta 1. This is the original path. This is the original path of my light. At the interface, it is going to bend. It will bend either towards the normal or away from normal. Okay, let's find out. mu1 sine theta 1 is mu2 sine theta 2. Okay, I hope that you are able to see clearly all of this. Okay. Do you see this clearly? I hope. Now, if mu decreases, then sine theta increases. Okay, theta increases. Mu times sine theta is constant. If mu decreases, sine theta has to increase. If mu increases, sine theta has to decrease, such that the product remains constant. That means this angle is going to be larger. Mu has decreased. Denser medium, rarer medium. Light is going from denser to rarer. Mu has decreased. Theta must increase. Okay. So theta 1, theta 2 is more than theta 1. Okay. So this will be angle. Okay. This is how the light will be refracted. This whole angle is theta 2. This was the original path. Now the light bends away from normal. This is deviation. This is deviation. So in this special case, light going from denser to rarer medium bends away from normal. And that's it. Okay. We are going to do a lot of problems based on this concept only. Ready for that? Lots of problems we are going to do in this class, remaining time. Next class also, after that also. Okay? Snell's law. These special cases you should remember, keep in mind. Okay? Let's start with problem. First question. Find angle of deviation. Find angle of deviation. Okay. Let's say that I have two mediums. One is air. The other medium mu is root 2. Two mediums. Okay. Light is incident like this. Let's say that this is my light. Traveling in air. It starts entering into the other medium at this point. This angle is 45 degrees. Light will bend. What will be deviation? Find out. Okay. Second. Okay. I have two mediums. Medium 1. This is medium 2. Okay. Two mediums are given. I have light here. This is light. Its wavelength is 5000 angstrom. 5000 angstrom, lambda 1 is 5000 angstrom. Okay. This mu1 is equal to 2 this angle is 30 degree, okay, and this angle here is 60 degree, okay. This is lambda 2 and this medium is mu 2, okay. Find lambda 2 and mu 2. Can you do that? Okay, let's do these two problems, then we are going to do a few more if we have time. What do you think? Can you do it? Of course we can do it. Very simple. Okay, very simple. It's just mu1 sine theta 1 is mu2 sine theta 2. Just remember one thing, theta 1, theta 2 measured from normal. Okay. Sometimes we discuss it, call it angle of incidence and angle of refraction. But that does not really make much sense. Okay, let's say that that is not required. Of course, it makes sense. It does make sense. Angle of incidence and angle of refraction. But you see, it's like this. I have some angle. This is my light. Okay, this is my common normal here. Okay, this is theta 1 and this is theta 2. Which is angle of incidence and which is angle of refraction? Angle of incidence, angle of refraction. Makes sense. This is mu 1, this is mu 2. Mu 1 sin theta 1, mu 2 sin theta 2. Snell's law. Remember reciprocity. What will happen if I start sending my light in this direction? I can reverse the direction of light. Then all the directions are going to be reversed from beginning till the end, from end till the source beginning. Okay, so this is also going to be reversed. So what was the angle of reflection now becomes angle of incidence. What was angle of incidence now becomes angle of reflection. So it does not really make any difference. Okay, so it's better to talk in terms of theta 1 and theta 2 than talking in terms of angle of incidence and angle of reflection, because you see this is reciprocity. This is nothing but reciprocity. Okay, the entire path of a light can be reversed exactly. It is going to follow the same path in reverse order. Okay, so what was angle of incidence becomes angle of refraction and vice versa. Okay, so that's why we talk in terms of theta 1 and theta 2 only. We do not talk in terms of I and R. Okay, we did that in junior classes, but let's not do that here. Okay, so it's like this. This is air. This is air. So mu is 1. Okay, this is 45. So this also becomes 45. We actually have to take this angle from the normal. From the normal. Okay. In the other angle, there is going to be some theta. I do not know what it is going to be. I have to find out. This mu is given root 2. What I will do, I will write 1 times mu 1 sin theta 1 sin 45 is equal to root 2 times sin theta. And that's it. That's my answer. 1 over root 2 is root 2 sin theta. Sin theta is half. Theta is 30 degree. This angle is 30 degree. Okay. This was the original direction. And do you know why this is 30? Why this is smaller than 45? Because this is a denser medium. Light is going from rarer to denser. It is going to bend towards the normal. Okay, it is going to bend towards the normal. What will be this deviation? This whole thing is 45. This whole thing here also is 45. So this is going to be 45 minus 30, 15 degree. This will be deviation in this light. Answer this. That should also be simple. Okay, but you have to be careful, okay? Otherwise, you are going to make some mistake. Angles we are going to measure from normal. Angles we are going to measure from normal. Okay? Can you find the answer? Can you find it? In the meantime, let me write one more problem here. A very interesting problem. Very, very interesting. It's like this. Okay. I have this glass sphere. Glass sphere. Mu is equal to root 3. Mu is root 3. This glass sphere. This is the center of the sphere. A light is incident like this. You see, this is normal. Light is incident like this. This is 60 degree. Okay, understand? Find angle of emergence and net deviation. Note down these two problems. Okay, we are going to solve it now. Now we are going to solve it. Okay, you know how to study. Okay, you have to pause the video from time to time. It's 1 hour lecture. You may well take 2 hours to complete it. Okay, you understand this. Do not watch it like a movie. I keep reminding this thing again and again. This is not entertainment. Okay, this is not entertainment. Do not watch it like a movie. Do not watch it to pass your time. It's like, okay, you know what I want to say. Anyway, so this is the interface. This is the interface. At this point, light is changing the medium. This point here. First thing we do is to draw a normal, because I have to measure the angles from normal. Angles from normal, okay? So this angle here will be theta 1, this will be 60 degree. And the angle here, okay, this is lambda 2. The angle here will be theta 2, this will be 30 degree. I have to find lambda 2 and mu 2 both. The refractive index of this medium and wavelength in this medium. Both I want to find. Okay? So Snell's law. Snell's law. Snell's law. What is Snell's law? Mu 1 sine theta 1. Mu 2 sine theta 2. Okay, mu 1 is given. Mu times sine 60 is mu 2 sine 30. Okay, so 2 times root 3 over 2 is mu 2 times half. Okay, I have this answer. 2 root 3. 2 root 3. Okay, it's 2 root 3. What about wavelength? We just discussed few times ago. When light goes from one medium to the other medium, or many mediums, one by one, okay, then we have mu times v is constant, mu times lambda is also constant. And understand this. Mu1, v1, mu1 sin theta 1, mu1 sin theta 1, mu2 sin theta 1. Mu1 v1, mu2 v2, mu1 lambda 1, mu2 lambda 2. The product of refractive index with sine of this angle going to remain constant. Product of refractive index and speed in the medium remains constant. Okay. Similarly, mu times lambda remains constant. Okay. So here mu, that means mu1 lambda 1 is mu 2 lambda 2. I have this answer. 2 times 5000 angstrom is 2 root 3 times lambda 2. I have this lambda 2. It is 5000 over root 3 angstrom. That's my answer. Okay. This is the answer. Now the last problem. Very interesting. Okay. Like laws of reflection are applicable for any surface, plane surface or curved surface, spherical surface, parabolic surface, any kind of surface. Snell's law is also applicable at any surface. You just have to draw the normal at point of incidence. Even if I have a surface like this, I have a surface like this. I have air here, I have water here. I have this kind of surface. And water is incident here. Let's say the light is incident like this. Here also, what I will do? First I will draw the normal. This is my normal. At this point of incidence, okay? Find this angle, theta 1, okay? Now the light is going to deviate. Light is entering a denser medium from air to water. Why? Because water is more density? No. Because the refractive index of water is more. That's why. Okay? It is going to bend towards the normal like this. This is how it is going to bend towards the normal. And Snell's law will be applicable. Same thing will happen here also. Try to get the answer, okay? Try to get the answer. Very interesting. What I have to find? The light is finally going to come out. It will enter the glass here. Finally it is going to come out like this. This is known as angle of incidence. Angle of incidence. From here also it is going to come out. This is angle of incidence. This will be angle of emergence. Angle of emergence. Light is emerging from here. And then I have to find a deviation. Light was going in this direction, and finally it is coming out in this direction. This is the angle of deviation. This we have to find. Can you find it? Okay, let's find it. Let's not leave it for the next class. You want to leave it for the next class? Then you pause the video, wait for one day, you start from here, resume from here, okay? It will become a problem for the next class for you. Okay, let's do it here now. Okay, so it's like this. Okay, this much big sphere is not required, it's just for the sake of clarity, you see, so that you can see all the angles clearly. This is my point of incidence here. This is my point of incidence. Okay, this is 60 degree. This is the original path. Outside is air. Outside is air. It enters into a denser medium. It is going to bend towards the normal. This is normal. Center joined with this point of incidence. This line becomes normal. It is a normal line. Light is going to, this is the original path. It is going to bend towards the normal because it enters a denser medium. It is going to bend like this. Let's say that this angle is theta, angle from normal. This mu is √3, mu is 1 here. I will write 1 times sine 60, √3 times sine theta. Okay, this is √3/2 is √3 times sine theta. Okay, what is sine theta? Half. What is theta? 30 degree. That means this angle is 30 degree. 30 degree. This is the deviation. This is deviation, delta 1. What it will be equal to? It will be equal to 30 degree. Okay, 60 minus 30 is 30. At this point again medium changes. This point I have glass, the other medium is air. Again there is going to be refraction. I will find the normal. Okay, this is my normal. This is my normal. Normal. Okay, this is the original path. original path of this light. Now this is going to change, deviate. Light is going from denser to rarer medium. It will bend away from normal. This is the original path. It is going to bend away from normal. Okay, it is going to bend like this. Okay, this angle is 30. This is radius. This also is radius. So in this triangle, these two angles are going to be same. If this is theta, this also will be theta. This also will be theta is 30 degree. Do you understand this? You understand this? Now what will be this angle? This is the angle from normal. This will be angle of emergence. What will be this angle? Okay, let's say that it is equal to E. E is angle of emergence. Now apply Snell's law here. Wherever there is refraction, at that point we apply Snell's law. I applied Snell's law at this point here. I will apply Snell's law at this point here. We apply Snell's law at a point where refraction happens, where medium changes at that point. Here, I will write Snell's law like root 3 times sine theta, sine 30 is going to be 1. It is air, this is air, use 1, okay, times sine E, okay. So this is root 3 times half is sine E. Sine E is root 3 over half, root 3 over 2, E will be 60 degree. Okay, so this angle is going to be 60 degree. This is angle of emergence. And by the way, these two angles are always going to be same. Do you know why? See, this is 60. Angle in air is 60. If angle in air is 60, angle in glass is 30. Angle in air 60, angle in glass 30. Angle in glass 30, angle in air 60. That's why this angle is always going to be same as this angle. Always. Okay, do you understand this thing? Okay. Now, so what about deviation? This was my original path, and finally light moves in this direction here. Okay. So this is going to be my deviation. Can you find it from geometry? From geometry, this is 30. That means this angle is also 30. 30. Okay. Now, this angle here is 30. This angle is 30. This angle is 60. This whole thing is 60. That means this whole thing is 60, because this is 60. Out of that, this is 30. That means this angle here, this also is 30. Okay. Now look at this triangle here. This triangle. Okay. This angle, which is our angle of deviation, which is what I want to find. This is an external angle for this triangle. External angle. This is going to be equal to this plus this. This angle 30 plus this. So it is going to be equal to 30 plus 30 is equal to 60. Okay. This is one thing. We got this angle using geometry. Now let's look at the deviation produced in each step. Each step. This is the first deviation. Delta 1 is equal to 30 degree. Deviation in the first step here. First deviation. Now the same light ray deviates again. What is deviation here? This deviation, delta 2. Delta 2 is equal to 60 minus 30 is 30 degree. This whole thing is 60. Out of that, this is 30. So this is 30. This is 30. This is going to be 30. We studied this in mirrors, plane mirrors. When a light ray undergoes successive deviations, then net deviation delta is going to be delta 1 plus delta 2. If a light ray undergoes successive deviations, the net deviation will be sum of all the deviations. This deviation is 30 degree clockwise. You see, this is clockwise. This also is clockwise. Both are clockwise. So this will be 30 degree clockwise plus 30 degree clockwise. This is 60 degree clockwise. They are always going to be same. You get it by simple geometry or you get it using this relation. That in case of successive deviations, net deviation will be equal to summation of all the successive deviations. It is applicable everywhere, for mirrors, for lenses, everywhere. Okay, so that's it about this class.